In this video, we're going to look at two lemmas and an identity. The envelope theorem for unconstrained optimization is the first thing we're going to look at. Consider two choice variables and one parameter, where we want to maximize utility as a function of goods x and y and a parameter theta. The first order conditions are that the partial derivatives of the objective function with respect to the first good, if you like, we call it good x here, is equal to the first partial derivative of f with respect to y, and they're both set equal to 0. This is a result we've had before. If the second order conditions are also met, we find that x star, the optimal x, is a function of the parameters theta, and the same thing for y as a function of the parameters as well. And these we've called the ordinary demand functions. We substitute those back into the objective function and we get the maximum value function v as a function of theta, as shown here by the function as a function of the optimal x's and y's, which are now a function of these thetas. The value function is also known as the indirect objective function. So we want to differentiate v with respect to theta. And when we do that, we get the partial of f with respect to x multiplied by the derivative of x star with respect to theta, plus the partial of f with respect to y multiplied by the derivative of y star with respect to theta, plus the function f partial of f with respect to theta. Now, because of the first order conditions, which we had up here, these first order conditions, which we repeat here, this means that f of x and f of y is 0, so all we're left with is this f of theta. So the first derivative of the value function with respect to theta is just equal to the partial of the objective function with respect to theta. And we know this as the envelope theorem. This is called the envelope theorem. And this is a quick derivation of it. Now, consider the profit function. So here we have an unconstrained maximization problem. Profit is price times the production function, f of capital and labor, minus the wage times the amount of labor, minus the rental times the amount of capital. So W and R are the input prices. We find that the first partial derivative of the profit function with respect to labor is equal to the value of the marginal product of labor minus the wage rate equals 0, and the same for capital, the marginal product of capital minus the value of the marginal product of capital minus the input price of capital is equal to 0. And from that we derive these input demand equations, L star as a function of output prices and these input prices, and K star as a function of output price and the input prices. So we substitute that back into the profit function, and we get that profit is a function of prices and the output prices and the input prices. So P times the production function with the optimal amounts of capital and labor in them, minus the wage rate times the optimal labor, minus R K star is going to lead to the maximum profit. And this is called the indirect profit function. What is the effect then of a change in the wage rate on profit? Well, to find that, we first differentiate the direct profit function with respect to W, to the wage rate, and we get the partial of the direct profit function with respect to the wage rate is negative L. Since the indirect profit function, which is this term here, is the maximum value of profits for any values of price, wage, and rental, changes in the maximum value function for profits from a change in the wage takes all capital for labor substitutions into account. Thus, we get that the partial of the indirect profit function with respect to the wage is equal to this value the marginal product of labor minus wage times the partial of the optimal labor function with respect to the wage plus the value the marginal product of capital minus the input price of capital times the partial of the optimal capital function, input demand function with respect to the wage. So this part takes into account this capital for labor substitution and then minus L star. So what we do is we find that these are 0 from first order conditions, and we can get that when we take the derivative of the indirect profit function with respect to the wage, we get the negative of the labor function, and the same thing for capital, we get negative of the capital function. So what we've done is we've got the derived input demand functions, we've recovered them by taking the derivatives of that indirect profit function with respect to the inputs. If we do it with respect to the output, what we do is we get back the production function, which is simply Q, or output. Now these three equations, these here, are known, or they constitute what is known as Hotelling's lemma. All right, so that's for Hotelling's lemma applies for the case of unconstrained maximization, or I guess you could say minimization as well, because we can multiply the objective by minus and then maximize it, and then basically we're minimizing. The envelope theorem for constrained optimization is a bit different, but along the same lines. We demonstrated in the previous video and done in Dixit chapters 5 that the maximizing utility as a function of x, y, and these parameters theta, and I'm using a semicolon here to offset the theta from the x and the y, subject to g x of y theta. These are the parameters, these are the choice variables, x and y are choice variables. We form the Lagrangian. Notice that we have that 0 here, and we put a negative there because we do not have a constraint C like we did in Dixit. We'll come back to that in a minute. The maximum value function in this case, we denote V as a function of theta is equal to F. We substitute in the optimal values for X and Y denoted by stars and a function of theta each. And of course, we've still got that theta there to as well. So what we've done is we've put in these optimal values here and this one here, and we've got theta, and that's equal to U star. Remember that by the envelope theorem, the maximum value function and this U star, which is the direct utility function, they're tangent at that point, which is the point that we're looking at here. So if we take the derivative of V with respect to theta, we get f of x dx star, the partial of x star with respect to theta, plus f sub y, which is the partial of f with respect to y, times the partial of the optimal y star with respect to theta, plus f, the partial of f with respect to theta as well. But in this case, because we've got constrained optimization, f sub x and f sub y are not equal to 0. All right, because of the constraint there. Rather, we have to take the derivative so that the derivative of v with respect to theta looks like this. And if you look at this particular function, what you'll see is that first order conditions for constrained optimization say that that has to equal 0. This one has to equal 0. So what we're left with is basically f, the partial of f with respect to theta minus lambda g theta. But let's call this L theta. All right. If the constraint was given like this, where we had a right-hand side cost here, then we would find that the Lagrangian with respect, the derivative of the Lagrangian with respect to c is identical to lambda star, the Lagrange multiplier, or the shadow price. All right, whereas here, the partial of the Lagrangian with respect to theta is equal to f theta minus lambda g theta. So that was clearly shown in chapter 5 of Dixit. Now, if we look at consumer theory, we substitute the Marshallian demand functions into the Lagrangian. So here we substitute them into the utility function, and this would give us the indirect utility function. But we're going to do it just a little bit more. We're going to also substitute it into the constraint set. So we get this, and that means we have this value function, which is a function of the parameters p1, p2, and m. So we take the partial of the value function, the maximum value function with respect to p1, and that gives us the marginal utility of 1 minus lambda, the price of 1, multiplied by the partial of the Marshallian demand function with respect to p1, and we get the same kind of result for the second good, where we get marginal utility of the second good minus lambda times the price of the second good, that whole expression multiplied by the partial of the Marshallian demand for the second good divided by, or with respect to p1. Then we get back the budget constraint, which would turn out to be 0, multiplied by the partial of lambda with respect to p1, and we end up with minus lambda times the Marshallian demand for Q1. So when all was said and done here, because of these first order conditions that have the marginal utility equal to lambda p1, marginal utility of 2 is equal to lambda p2 by first order conditions, and because this is equal to 0, m is your budget, your entire budget is spent, so therefore this term goes to 0, this term goes to 0, and this term goes to 0. So what we're left with is this part of the result, and we get that partial of v with respect to p1 is equal to minus lambda times q1 star, where q1 star is the Marshallian demand function. Now if we take the partial derivative of the maximum value function with respect to the budget m, we get a similar result, except this time when we multiply the marginal utility minus lambda of times p for that particular good, we take the partial of that good with respect to the budget or income, and we see that it comes out like this, and we also end up with this lambda here. But again, this term, and this one all go to 0, so in the end the partial of v with respect to m is equal to lambda due to those first order conditions. Now taking the ratio of the partial of v with respect to p1 divided by the partial of v with respect to the budget or income, we get minus lambda q1 star from this expression here. And let me just highlight that with a red pen. So we have this one, and we have that one, we take the ratio of those two, which we do here, and we see that we get minus Q1 star, which is the Marshallian demand. So rearranging that, we get that the Marshallian demand function can be recovered by taking the negative of the partial of the value function with respect to P1 divided by the partial of the value function with respect to M. Now, it doesn't really matter if we use the Lagrangian to find our maximum value function. In other words, if we plug in up here the Q's, the Marshallian demands into just the indirect, into the utility function rather, to find the indirect utility function, or whether we put it into the entire Lagrangian like we did here. That doesn't make any difference. So now the final one is Shepard's lemma. Recall the minimization problem that we'd been looking at, where we minimize the prices, sum of the prices times quantities, subject to a particular level of output or a particular level of utility, a particular indifference curve, where P and Q here are vectors. Upon substituting the Hicksian compensated demand functions that we derive when we do this minimization subject to a particular indifference curve, we get the Hicksian or compensated demand functions. If we plug those back into the objective, we get that M is a function of P and U, and we call that function E because it's the expenditure function. But again, what we could do is it's possible to substitute the compensated Hicksian demands into the Lagrangian to get the expenditure function, in which case we have an expenditure function that looks a little bit different, but it's still a function of P and U. But here it's P times QC, where the C represents the optimal Hicksian or compensated demand, and lambda C, the same thing. It's related to the minimization problem. And here what we're going to do is we're going to denote U with a little 0 there as a superscript to indicate that this is a particular parameter. It's a fixed indifference curve that we're on. And you can think of it, it doesn't need to be an indifference curve. It could also be isoquant. So we take the partial of the expenditure function with respect to Pi to one of the goods. We get this result here that we have the price of I minus lambda times the marginal utility of I multiplied by the first derivative of the compensated demand function with respect to Pi. And we do the same thing for some J good, and we could get, basically we have to sum these. We could have, if we have 10 goods, we'd have 10 expressions like this, and each expression, the partial derivative would be with respect to the same Pi. And then of course we have this result, and what I need to do there is put in the little U0. All right, so we get this expression here, plus we have this derivative, this falls out as well. All right, and you can remember that by just think, where does this come from? Well, if this is PQ, what you do is you take the first derivative with respect to P, gives you QC, and then you have P times the first derivative of QC with respect to P. But it's this one here, when we take that derivative of this little component, we get just the QC back. So what do we do? Well, if we take the partial derivative of the expenditure function with regard to any price, we get the Hicksian or compensated demand function back from that expenditure function due to those first order conditions. If we use the expenditure function again and looked at it with regard to the indifference curve, whether we're on that U0 or some higher one. So if we go to a lower or a higher one, that's denoted by this small change here. We get this expression. We take the derivatives now of the Q's, the various Hicksian demands with respect to this parameter, and we do the same thing here for the constraint. Again, we have this result plus this lambda c comes out for the simple reason that, again, we have this multiplied by this here, and we have one derivative of this one. So we have lambda c times u of 0. So in one case, we have the lambda c times the derivative of u0 with respect to u0, which is 1, which gives us this lambda c. And then we have also the derivative of lambda c times u0. So in effect, this term and this term go to 0 because of the first order condition, and we end up with lambda c. So these results are known as Shepard's lemma. So these results, this result that if you take the first derivative of the expenditure function with regards to any price, gives you the Hicksian demand function for that commodity, and if you take the partial derivative of the expenditure function with respect to u0, then you get lambda c. And remember, lambda c tells us how much the objective function changes when you make a change in the constraint. In this case, the constraint is the indifference curve you're on. So these are known as Shepard's lemma. Thank you for watching this video. There are many more videos in this 2 to 3 course series. A list of videos, the order in which they should be taken, and links to them are found under Mathematical Economics at the website indicated below.